lecture in aerodynamics we had in previous sessions, you learned that the aerodynamics of a wing can be expressed in the form of a single equation. So we call this equation as lift drag polar. Where is this laser pointer? Yeah, the lift drag polar. So this equation actually tells us that the drag coefficient consists of two elements. A lift independent part, which is zero lift drag, and a lift dependent part, which we call it as induced drag. So this shows that even if there is no lift, there will be some drag, and we call it as, for example, a friction drag. So this is essentially the same as when you are, for example, driving your automobile. You don't generate any aerodynamic lift, but you actually experience drag force, aerodynamic drag. Now, when a three-dimensional finite wing generates some lift for you, something interesting appears, and it is the tip vortices, tip vortex. So this is due to the pressure difference between the upper and lower surfaces of the wing, and because of this pressure difference, air starts to flow around the tip of the wing, the tips of the wing, in a circular motion from lower to upper part, and this creates wingtip vortices. So when an aircraft flies past, it leaves tip vortices in the air, and you can imagine that these vortices contain some kinetic energy, and this is essentially the cause of aerodynamic drag. But if you consider a two-dimensional case, because there is no tip vortex, there is no lift-induced drag as well. So this is very important to keep in mind. So let's have a look at the equation that relates the lift to the drag, and the lift drag polar equation actually. There is a parameter called A in here, and in this equation you see we call it as aspect ratio. Aspect ratio describes how slender your wing is. So it is b squared, or a squared of a span divided by the area of the wing. So if the aspect ratio is high, the wing is approaching to a two-dimensional wing, and for example, the gliders have a very large aspect ratio. And besides, you see another parameter, it is phi in here, and it is called the span efficiency, and it is actually a measure for the distribution of lift over the wing. So if there is an ideal case when we have a perfect three-dimensional wing, it is actually equal to 1, in ideal case. Now, in the current lecture, we actually are not interested in drag of let's say two-dimensional wing or airfoil, or even not drag of three-dimensional wing, but we are interested in the drag force of a complete aircraft with all its compartments. So the wing by itself is in fact three-dimensional, and therefore it has some lift-induced drag, as it is represented here. This is a part for the wing. But all the other parts of the aircraft, such as the fuselage, the antennas, vertical stabilizer, everything, they also have some lift and drag contribution. And for the drag part, we call it as a parasite drag. If we remember, we said it before. For example, if the fuselage is placed at a zero angle with respect to the flow, it will have a certain amount of drag. We call it a parasite drag of fuselage. And in addition, this drag will change if we place the fuselage under some angle. It could be both side slip angle and angle of attack. And in addition to the drag force, the fuselage or other compartments generate also some lift force. So if you add, that's why we are having the summation symbol in here. If you add these effects to our lift drag polar, it will mainly, as you can see, shift to the right. So in other words, we have more parasite drag for more or less the same lift force, as you can see. So this curve you see in here still resembles the parabolic equation that we just saw in the lift drag polar equation. You can see that clearly if you create a graph in here. Instead of using CL, you are using CL squared. Here you can see that the lift drag polar of a real aircraft, which is this black line, and the parabolic equation, which is this a straight dashed line. So basically you can still use the lift drag polar, and now we use what we call the Oswald efficiency factor. So if you remember here, we had this phi, but in aircraft, when we are talking about the whole aircraft, we replace phi by E, and it is Oswald efficiency factor. And he was working in NACA, the predecessor of NASA. So this factor E, as we said, is instead of the wing efficiency. So we use the complete aircraft. So in this case, the non-zero lift drag is will be also larger. This zero lift drag will be also larger than that for the wing case, the wing only case. So this CD0 and this CD0, these are not the same amount. This one is written for a wing, 3D wing. This one is written for a whole aircraft. So in reality, instead of using a parabolic equation, this parabolic equation CD0 plus CL squared over pi aspect ratio E, in reality we use a two-term drag polar. So this is more accurate, a bit more accurate, and because we need this accuracy when we are actually facing the real world problems, when just decreasing the drag force by 1% would be very beneficial for us and would be very significant. So it seems very pretty cool because we have a very simple equation that completely describes the complex aerodynamics around the aircraft, but we have to go back to our original problem. We want to describe the aerodynamic forces as a function of airspeed and the flight path angle gamma, and by doing so we can simplify the equations of motion, and finally we can solve these equations of motion. So the lift drag polar does not give forces, as you see. It gives the coefficients. So in here you see the coefficients. So in order to make them make the coefficients as forces, you have to multiply CD by half of rho v squared s. So if you just use the complete form, I mean the more accurate form of the drag polar, and just replace the x's with CL and y is CD, and then using the definition of the drag force, you can come up with this equation in here. So as an exercise, you do it yourself. It's not very complicated. So you will see that the latest equation, the drag, is only a function of v squared plus another function of 1 over v squared. So this way you could actually express the drag force as a function of only velocity, which is pretty cool. So in here we are one more step to our final objective. So again, you can do it for other forces like the thrust force, for example. So the thrust force, any air breathing engine, as indicated in here, regardless whether it is a propeller or a turbofan or pure jet or a helicopter rotor, functions according to the same principle. So as you have some mass of air that is accelerated to very higher velocity, and as a result a force is created, this thrust force, according to the equation of momentum. And if it is a steady flow, you write the equation of momentum for a steady flow from Newton's second law. Therefore, you can represent all the proportion types with this very simple schematic representation. So in steady conditions, the inflow velocity of air, this V0, equals to the flight speed of the aircraft, and the velocity behind the aircraft equals to the jet velocity, Vj, and the mass flow of air through the engine is actually shown by m dot. So in most propulsion systems, there is some fuel, m dot fuel or m dot f, that is burned, and thus the mass flow at the exit in here is the summation of m dot plus m dot f, as you see in here. But based on the momentum equation, you can state that the thrust force is equal to the change of momentum at exit and inlet. So at exit, the momentum is the summation of mass flows times the velocity at exit, and at the inlet is the mass flow rate times velocity at inlet. So this results actually is valid or holds if there is no pressure difference at the inlet and outlet, okay, which is this pressure term in practice is often much smaller than the momentum term. So we can neglect the pressure as well. And one more thing that we can neglect is the mass fuel of flow, because it is much smaller than the mass of air, and you can again neglect the m dot f, and hence you can write the thrust force. This is a very simplified version of thrust force, which is the mass flow rate of air that is passing through the propulsion system times the difference of velocity at the exit and entrance. So, in essence, there are two fundamental options to create the same amount of thrust. One can take a little bit of air, little bit of air meaning a small m dot, and accelerate it to a very high jet velocity. So this difference is very big. Or you can inversely take a very large amount of air, so a large m dot, and then accelerate it to not very high jet velocities, a small acceleration. So this a small acceleration with a high value of air is actually done by propellers, and the way that we use a small mass with a high difference in jet velocity, you will see it in the jet engines. So if one asks, okay, that these two are generating the same amount of thrust force, so which one is better? So to actually have an answer about this question, we have to define the efficiencies in propulsion system. So if you consider an aircraft that is flying from point A to point B with some specific velocity v, so it's apparent that you have to generate some thrust force, this thrust force T, and it has to be created by the engine in a time interval of delta t. So it starts from t0 to t0 plus delta t. The aircraft goes from point A to B, so this is the delta x meters, for example. So you can define here the energy that is required to travel this distance. So in high school you have learned that by the principle of work, the energy needed equals to the distance multiplied by the force, right? So if you just divide everything by time, then you will come up with the power. So the energy per second is power, and it is equal to the thrust force times the velocity. Velocity is the delta x divided by delta t. So if you take the time interval very small, so this delta t, if it is very small, so then the thrust becomes then the power becomes thrust times velocity. So we call this power as power available. Just remember, we want to define some efficiencies to find out whether propeller aircraft is more efficient, or a jet aircraft is more efficient. To do so, we are defining some efficiencies. So, in order to create the thrust, we need to provide power, and the power is actually coming from burning fuel, for example. So we call this power as thermal power, and we show it by Q, and it is equals the mass flow of fuel which is burned multiplied by the amount of heat or energy that the fuel gives to us. So, or multiplied by the energy that it is contained in 1 kilogram of that fuel. So it is a constant chemical value. We call it as H. So amount of energy per unit mass of fuel. So the total efficiency, as you see in here, eta T, is nothing but power available divided by this thermal power. So this is actually every time, everywhere, this total efficiency is smaller than 1. So you cannot reach more than 1.